check this out. We're going to do an inclined plane. And here's what we're going to be talking about. We're going to talk about maybe, I don't know, how's about just a simple block sliding down a little triangle. Imagine if you had like some kind of plane that was like this, and I just had the pen sliding down like that. Pretty simple, pretty straightforward. But the hard part is kind of the trigonometry of this. So let's take a look at this real carefully. This would be angle theta. What forces do you see acting on this thing? Catherine?
Gravity.
Catherine?
The weight.
The weight, yes, exactly. Not the force, or it's not gravity, it's not the force. The weight is the force. All right, what other forces do you see acting on this object?
What, sorry?
What other forces do you see acting on this object? There's got to be some other force, because if not, then this thing would actually just kind of fall straight down. There's some other force keeping, or the what? The normal force, exactly. Yeah, some people call it natural, so I'm not going to correct you with that. But some people call it natural force, some people call it normal force. I think I always taught normal force, so I'm going to stick with that. All right. If there were, I'll tell you one thing, is if there were friction acting on this thing, which in every real day object, there's actually is friction acting between the pen and the wood, it would act kind of up at an angle like this. You see what I mean? And not only that, but as this thing slides down, gross, sorry. As this thing slides down, it slides down at this angle, kind of over here. So here's the problem is, I'm not a big fan of using SOHCAHTOA. I mean, I know how to do it, but if I could get away with a clever way of not having to do it, I would much rather do that. I would much rather take that route. Does that make sense?
Yeah.
All right. So what I'm going to do is I'm going to take my coordinate system. Right now, what is aligned with my coordinate system? Say that this is my coordinate system. Here's the x and the y axis. What are the vectors that are aligned with this particular coordinate system? It's only the w. It's only this thing that is going down in this direction. But if I were to take my coordinate system and turn it, say like that, then the normal force is aligned exactly with my y direction. You see what I mean? And the acceleration is aligned exactly with my negative x direction, but I can always call that the positive x direction. And if I had a friction force, that would be aligned exactly with the x direction. What force do you see is not aligned with this new coordinate system?
W.
The w, exactly. So here's the thing, here's what my point is I would rather break up the w into its components and have a coordinate system that works like this than have a coordinate system that goes standard, like what I'm comfortable with, but have to break up this thing into xy components, the frictional force into xy components, and the acceleration into its xy components. I don't even actually know how to do that, to be honest with you. So the easiest thing for me to do,
Friction, right?
what is that?
We don't have to do friction, right?
No, we don't have to do friction, but I'll tell you one thing is I'm going to add it in chapter 6. And I'll be honest with you, it's not that bad at all. But what I would rather do is I would rather take this coordinate system and kind of slant my head. If that makes you uncomfortable, just turn your head like about 45 degrees, and then you realize, hey, everything's straight now. The only thing is this thing's no longer in its components. So the trick that I'm going to need to show you is how do I break this into its components? How do I break this w into its components if my new coordinate system were slanted like that? And I think that the best thing to do would be some trigonometry. It's not even trigonometry, it's actually just geometry. The question is, if this is theta, then, and this is w, it goes straight down here. Let's make a dotted line over here. This means this is perpendicular right here, okay? What is this angle right here? That's what my question is. If that's theta, what is that angle?
It's equal to 90 minus theta.
Is that what you think?
That's what I said.
Yeah.
Well, because
All
the
right.
triangle is 180, and so 180 minus that 90 degrees is 90.
All
So
right.
those two angles left have to equal 90, and then that one is equal to.
I would argue this actually. You know what? I'll take your approach. It wasn't how I was going to do it, but let's talk about that. I would say that guaranteed this is 90 minus theta. This angle right here. Right?
Yeah.
This one's equal to 90 minus theta. Because if I were to extend this thing out, this is a right angle right here. You're right, a triangle adds up to 180 degrees, so 90 plus theta plus 90 minus theta is equal to 180 degrees. If this, I told you that this is actually a right angle as well, you know, I showed it right there. Then what happens is this angle is 90 minus 90 minus theta. Does that make sense?
Yeah.
So this is actually 90 minus 90 plus theta. Distribute the negative. This is just theta. This angle right here is theta up there. Does that make sense?
Yep.
All right. I'll quickly show you what I was going to do. What I was going to do is I was going to ask you, all right, if this is angle theta, and then this is w, what is this? Then what I was going to do is I was just going to kind of go like this, and then say, well, if that's theta, then that's theta as well. And if that's theta over here, that would make this theta as well. And I guess the best way I know how to do to take a look at that is I get a coordinate system and I go like this, and I say, well, if I'm going to move this up an angle theta and sweep out that area, I would actually, this stick will also move an angle theta this way. I don't know. I like your way better actually. I think from now on I'm going to teach it that way. But if this were theta over here, then I would need to break this up into its components, and this breaking up into its components would look like this. Still got my normal force. Then I have a Wy over here and a Wx. Because this thing is broken up into its x components, but my new x direction is in this direction right here. And this thing is broken up into its y components, but my new y direction is this one right here. W theta Wy Wx. What is Wx? Well, it's just using SOHCAHTOA. So I'm gonna actually, I'll do this the slow way, I don't mind. We have Wx is actually opposite over hypotenuse, so we're talking about the sine of theta is equal to Wx over W, so therefore Wx is equal to W sine theta. Similarly, Wy is equal to W cosine theta. Do you see that?
Yeah.
Alright, the only reason why I did this the slow way where I actually wrote out sine theta and then solved for Wx is because usually in almost every problem that I've given you so far, Wx is equal to W cosine theta. It's because the way we define the angle was we define the angle like this, right here. And then the x component would be your adjacent side, so when you talk about the adjacent and the hypotenuse, you use cosine. But in this case, the angle got defined up here. This is theta. If I gave you theta equals 20 degrees, 20 degrees would be up here. So in that case, your x value, your horizontal component, is actually the opposite over hypotenuse, so you would use sine of theta. It gets a little bit switched, but if you know SOHCAHTOA, if you know really how to do that, there's no problem here. I'm just showing you this because I don't want you, nor do I think that you do this in the first place, but I don't want you to blindly just say, oh, Wx is equal to W cosine theta. My answer is, well, that depends on where you call theta. If theta's down here, then you would have Wx equals W cosine theta, but if theta's up here, then you would have Wx equals W sine theta. Does that make sense?
Yep.
All right, cool. Now, I guess the question is, at what acceleration would this thing slide down the inclined plane at? All right. What I would do, the way I would go about doing that is I would just say, all right, well, the sum of the forces in the x direction is equal to mass times acceleration in the x direction. Is this thing accelerating in the x direction? By the way, I'm calling positive x direction to be going down this way. And the answer is yes, it is. So my acceleration in the x direction is simply Wx, because that's the only force that I see in the x direction, equals mass times acceleration in the x direction. So that would be W sine theta divided by m equals ax. And if you think about this problem, which is actually exactly opposite of what we had, because then we have force cosine theta over m last time. But if you think about this problem, all right, well, what is the sine of 0 degrees? Do you know?
No, I don't know.
All right, the sine of 0 degrees is 0. If you think about how the graph of sine looks like, it looks like this. You don't need to memorize that. I'm just, if you had a calculator or maybe if you had it memorized, sine of 0 degrees is 0. So if I plugged in theta equals 0, what would my acceleration be?
I don't know.
Well,
Wait, what?
if I plug in theta equals 0, that would mean the sine of 0 is 0. What's W times 0?
0.
Divide by m.
Yeah.
Still 0. All that's saying is, I had this pen on an incline, but if the incline were 0, watch that pen accelerate. Go. You see what I mean? It's saying this thing's not going to accelerate because your angle is 0. Now, if I had a small angle like this, then the thing would accelerate. If I had a really big angle like this, then this thing would accelerate. In fact, I can even go one beyond that. And I can say, well, what if theta were 90 degrees? So if theta equals 0, then ax equals 0. 0. If theta equals 90 degrees, the sine of 90 is 1. So that would be ax equals w over m. Does that make sense?
Yeah.
Well, w is actually mg, right? So ax is equal to g. That's what I'm getting. Does that make sense?
Yeah, that makes sense.
Well, yeah, and it actually makes sense physically too, because I mean, if you think about it, if your inclined plane was so inclined that it was 90 degrees, and you drop this thing, essentially, it would fall at the same rate or the same acceleration as if there was no wall there, because it's not even touching the wall at that point. Assuming no friction, that is. Right? If I were to put this pen against the wall and I say, what is the acceleration? Well, it would be the same as if I had the pen kind of in the middle of the air. Same acceleration. Gravity. We cool?
Yep.
Alright, cool. Now, what I like about this problem is it kind of, I'm going to go into kind of a math aside on this and kind of give you the history of what I think this problem is very relevant at. This W is actually mg. Let me just write this out a little bit more. So the m cancels, and your acceleration is actually g sine theta. Alright? The acceleration that this thing will fall down the inclined plane is g sine theta. Now here's what I like about this problem. There's this dude named Galileo. Have you ever heard of him?
Yeah.
He's a pretty awesome scientist. I'm a big fan. Anyway, he was in a church one day and he saw the chandelier. And so he saw the chandelier swinging back and forth. And he realized that this pendulum motion that the chandelier made is a constant time. And the only thing that will change that time is how long that pendulum is. The mass of the pendulum doesn't change it. The height that the thing starts off at doesn't change the period of this pendulum. Here's what I'm saying is that like the reason why he would think about these things is because back in his day they didn't have stopwatches. So how would they time experiments? They would use their pulse maybe. I don't know. Let's pretend they would use their pulse. Or maybe they would use a sundial. But the problem with the sundials is it takes so dang long that you can't measure seconds with a sundial. Does that make sense?
Yeah.
So he would use this a pendulum. He figured out how to use a pendulum because if you're using your heart rate and you're doing an experiment, all of a sudden some pretty girl walks by, like your experiment goes like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. You get all excited and all that kind of stuff. That's what the problem with using some kind of like biological clock. So he used this pendulum and he figured that out. Now, here's the thing. Here's the problem is he wanted to calculate out what gravity is equal to. He wanted to figure out the acceleration of gravity, but the problem that he ended up coming up with, or the problem that he had, was he had an acceleration and he dropped the pen or dropped the whatever he had, the weight, the mass, whatever, and it would fall too fast. Like imagine trying to use a pendulum to time this. See what I mean? Like if we had a stopwatch, we would be good. And that's what we do nowadays. But with a pendulum, you can't do that. So what Galileo did was he figured out, he knew that what he could do is he could put this thing on an inclined plane. And then what he could do is he could measure the acceleration because on an inclined plane, I can actually control the acceleration. If I want the acceleration to be 0, I would put it right here. If I want the acceleration to be small, I would only move this incline up a little bit. There we go. See that?
Yeah.
And I can easily measure that with a stopwatch. And I think he had a 16-foot inclined plane. That thing was 16 feet long. So it gave him some time to measure it. It gives him a more accurate reading. And he made that incline very, very small, so it kind of slid down. And I think he used like blocks of ice to reduce the friction. So what he was able to do is he was able to calculate this acceleration. Obviously, he knows the angle. So if you want to solve for g, all you would do is, okay, well, g is equal to a over sine theta. Essentially what he did was he diluted gravity, or he diluted the effect of gravity by changing the angle that he was dealing with. So that way it gives him something he can measure. And he ended up getting like gravity is equal to like, I think it was like either 9 meters per second squared or like 10.5 or something like that. He was only off by like 10%. So he wasn't even that far off, which is pretty good for way back then when you don't have a stopwatch or, well, I guess you don't have a stopwatch or a digital camera or whatever it is you would use to measure gravity nowadays. You see what I mean?
Yeah.
So what I like doing at this point, and I actually might have you guys do this, is actually do an experiment where you do repeat Galileo's experiment and actually calculate gravity for yourself using this concept of an inclined plane. But then again, I just told you all the answers, so I don't know how helpful that would be, but I think it's still interesting. Because oftentimes you don't get exactly what gravity is, but you get really, really close. So he was able to figure out what gravity is by measuring the acceleration. That was a little bit tough to figure out how to do. And then knowing the angle. The angle is pretty easy.